Hello everyone. Welcome to the sixth part of Modeling, Analysis and Design of PEB structure. I am Surajit Ghosh, and in this session, I'll discuss how we can assign a fixed, pinned or plate mat support depending on the base plate anchor bolt configuration and soil type. Till now, we have covered the modeling of mainframe members like column and rafter with tapered section, modeling of secondary members like purlin, bracing, and assignment of different member specification, member offset, release, beta angle, and tension compression only specifications which are required to adjust the alignment and define the load behavior of the members. I'll use the same model to assign the supports. For more details, you can go through this playlist on modeling, analysis and design of PEB structure. It is very easy to assign a support. We can simply select all the nodes at the base level and from the support page, assign a fixed or pinned support. But selection of support type and fixity level is quite complex. If the support condition is not assigned properly, that will affect the overall performance of the structure and increase the steel usage. So, we need to carefully select the correct support condition. For any concrete structure, columns are monolithically casted along with the foundation, whether it is an isolated, pile cap or mat foundation. The column or pedestal reinforcements are extended inside the foundation and tied with the foundation rebar. We can assume a fixity or moment transfer at the column foundation junction. That's why for any concrete structure, we assign a fixed support and consider the top of the foundation as the fixity level. But for any PEB structure, the steel columns are not extended or tied with the foundation. It is connected using a base plate anchor bolt arrangement, and it is very important to evaluate this base plate connection before support assignment. We need to finalize the level of fixity along with the support condition. Before going into the details, I want to discuss few basics, how the steel columns are connected to the foundation or pedestal and how the force is transferred from the column to the soil. I have briefly discussed about the support assignment in part 1.1. For any PEB structure, column base can be exposed or embedded within the concrete, but the columns are not directly connected with the foundation. There are few additional structural components which take part in the force transfer. First, the column load is transferred to the base plate, which is nothing but a thick steel plate with bolt holes covering the entire cross-sectional area of the column section. This additional area not only ensures better connection, but also provides a larger area for load transfer. Depending on the type of connection like axial or moment connection, area of the base plate might vary, and few additional components like stiffener or shear lug are provided to resist the load. I'll cover the base plate design later during connection design. This base plate is connected to the foundation or pedestal using anchor bolts. In general, steel columns are not extended below the ground. Rather, a pedestal is provided from the foundation till the column base, and all the required anchor bolts are tied with the pedestal reinforcement before casting. Anchor bolts play a vital role for the force transfer, which we'll cover during base plate design. In short, number and arrangement of the anchor bolt depend on the force or connection type. For example, if we want to transfer only axial load to the foundation, like a pinned connection, then the base plate anchor bolt arrangement looks something like this, where the bolts are placed within the flange. This base plate can only transfer axial load to the foundation and all moments are ignored. Whereas the second arrangement with bolts placed outside the section can transfer both axial and moment components and behave like a fixed connection. These two are the most common type of base plate, and depending on this, we need to assign the support condition. We need to assign a fixed support if the base plate is designed considering uni or biaxial moment. Pin type base plates are relatively cheap, easy to build and assemble in the site. Also, the foundation size reduces as the moment components are not considered during design. That's why it is commonly used in the industry. But there is one problem. When we assign a pinned support, we are releasing the moment at the support level, right? If a lateral load is applied on the structure, like a seismic load, it will try to rotate the structure. As the support cannot resist this rotation, we need to assign a higher section or stiffness to the mainframe to reduce this rotation and stabilize the structure. This will increase the steel usage, and reduced cost of the base plate and foundation will be nullified with this additional steel cost. Always keep this in mind during base plate design. Next, the level of fixity. For this, either we can consider the base plate level or the foundation as the support level. I normally prefer not to model the pedestal in the superstructure and consider the fixity level as the base plate level. During foundation design, we can design the pedestal along with the foundation using STAAD foundation. But if we want to design the pedestals manually, then we need to model this along with the superstructure. Also, if there is any brick wall along the periphery of the structure with height more than 5-6 feet, then a tie beam is required to support the wall and to reduce the differential settlement. To design the tie beam using RCDC, we can model it along with the pedestal, and for such case, it is better to consider the fixity level as foundation top. I think it is clear now how to finalize the support condition and fixity level. For this model, I have considered the base plate as fixity level, and I want to design the base plate and foundation considering axial load plus biaxial moment. From the front view, we can select all the support nodes, go to support, and from the support window, we can select and assign a fixed support. After analysis, we can export the support reaction and design any type of foundation in STAAD foundation or RCDC. There is another factor which affects the support selection: foundation type. It is not always possible to use an isolated foundation. Depending on the soil condition, load from the structure and structure type, sometimes we need to go for a pile cap or mat foundation. For example, if we consider any large plant unit with heavy equipment rested on the floor or an aircraft hangar, large amount of dead load is applied directly on the base slab, and for such case, an isolated or pile cap foundation is not sufficient. We must design a mat foundation. Now the question is, do we need to model the mat foundation using plate mesh along with the superstructure? Obviously we can, but it is not suggested. We know that a plate mesh increases the analysis time. If any iterative analysis like optimization or second order analysis is performed, for each iteration, additional time is required just to perform finite element analysis. For this PEB structure, we will perform steel optimization. Second order analysis might be required. So inclusion of a plate mesh will increase the analysis time. But this additional time is nothing but a waste, as in the initial phase of optimization, we don't require the support reactions. I normally suggest assigning a fixed or pinned connection at the base plate level for the mat foundation without modeling it along with the superstructure. Once the member and connection design are complete, simply export the model to STAAD foundation, where we can easily generate the plate mesh for mat foundation design. I'll cover this later during foundation design. We can also use the custom macro which I have developed to export the support reaction values directly from this model and use those for foundation design using manual approach or any other software. Still, if we want to model a mat foundation with plate mesh, then it is better to use the parametric model option rather than the normal plate mesh, as the support nodes are automatically identified in this approach. To model a mat foundation, first we need to generate the corner nodes of the mat. We can use the copy-paste, translational repeat or coordinate values to create these nodes. Next, open the parametric model. Add the mat boundary by selecting the corner nodes one by one, either in the clockwise or anti-clockwise direction. I'll define the name as mat, select the type as slab, and meshing method as standard, which creates a quad plate mesh with maximum plate size as 1.5 meter. We can modify this later. I have discussed all these options in the plate generation series. You can check those videos for more details. In the generated mesh prototype, we can notice that all the columns are considered in the mesh. Parametric model can identify the existing nodes during mesh generation. We can also generate a region with higher thickness if the applied load is high, like a machine foundation. If required, we can further modify the mesh size to a coarser or finer mesh. Finally, click on the Merge Mesh option to generate the plates. We can assign any plate thickness for analysis. Final thickness of the slab is determined during mat foundation design. This is how the model looks like with a mat foundation. In this modified model, I have already assigned the concrete pedestals, which are required if the column base is not directly supported on the mat foundation. As we can notice, steel columns are connected to the concrete pedestal, and by default, the base plate is considered as a moment connection. To assign a pinned base plate, we need to assign a moment release at this end of the column member. We are done with the modeling. Next step, assign the soil spring or pile support to this mat foundation. I will not cover the assignment of pile support in this video and assume that this mat is supported entirely on the soil. To assign a soil spring value under the support specification window, we need to use the foundation tab. There are two types of support: elastic mat and plate mat. Elastic mat can be used when a plate mesh is not available and only the support nodes are modeled. In this model, we have generated a plate mesh, so we can use the plate mat option. Select the direction as Y, which means we are assigning a soil spring in the vertical direction and other directions are fixed. If we define a Y-only mat foundation, that will generate an instability condition, which I have already discussed in the instability series. For any mat foundation, lateral movement is restricted by the soil, so it is better to assign the direction as Y. Specify the subgrade modulus value which is available in the soil report. Finally, assign this to all the plate at the base level. During analysis, program will calculate the influence area at each node and use the soil spring value to calculate the resisting force. Once again, this plate mesh will increase the analysis time. I don't prefer this approach, but I think it is better to know all the methods available for support assignment. After analysis, we can use the plate results for mat foundation design, either using STAAD Foundation Advanced or using RCDC FE or RAM concept. That's all. I didn't cover the mesh generation and plate mat support assignment in details, as these are already covered in my previous video. You can go through the mesh generation and instability series for more details. In the next part, I will cover the view management and group assignment for loading. See you in the next video.